Hello. This is Senthil here. I'm just checking who's the admin for today's session.
Hello, sir. Yeah, we will be starting the session exactly at 10:40.
A very good morning to all the presenters uh, and you can attendees of the session, along with session chair, Mr. Senthil. He is he is working with textile instruments, and he is an EDA technologist and a senior member of technical staff with TI. He is currently responsible for analog design reliability and system media solutions. He has more than 21 years of experience in the domain of reliability and system automation, standard cell I/O, high-speed DDR/IP design, and EST development. Here in this session particularly, there are a few specifics we need to know. So every paper will get 20 minutes, and this paper particularly will be so this paper particularly will be like out of the 20 minutes, 15 minutes will be there for the presentation and 5 minutes for the question answer session. And those question answer session will be handled by me. So if for 20 minutes are over or all the question answer are finished, we will move to the next paper. And this is the way we will proceed with the session. And now onwards, I hand over the session to Mr. Senthil for the further proceeding. Thank you.
Yeah, thanks, Professor Gaurav. Okay, hi. Very good morning and welcome everyone to the user design track session. We have 4 papers today. Let's get started. The first paper is early layout area and PLS estimation by designers. This is presented by Akshita. Akshita is a senior design engineer with ST Microelectronics with over 3 years of experience working on design automation and methodology. With the introduction, let's get started with the presentation.
Hello to everyone, I'm Akshata Bansal and today I'm going to present to you an innovative yet a very simple solution for early layout area and post layout simulation estimation by schematic designers. So in today's scenario, a handshake is required between the schematic designer and the layout designer for estimation of layout effects on the schematic design. This ECO can be very costly, especially for a sensitive design. It can take weeks of effort to stabilize the design when a significant sized design is involved. Also, we don't have an immediate feedback for the schematic design about the effects of layout on the schematic parameters. As you can see on the left hand side, today there's a multiple iteration involved between the layout designer and the schematic designer, where the layout designer sends back the post layout netlist back to schematic designer, who, based on post layout simulation, modifies the device parameters and sends the modified schematic back to layout designer for updated post layout effect analysis. This can take weeks of efforts on both layout and schematic designers' side to get an optimized and good quality product. We propose a methodology in collaboration with Pulsec team and with a tool that we call Animate Preview to eliminate this loop. So our methodology allows the schematic designer to generate a layout concurrently without actually having to make the layout. So the schematic designer can generate a layout and the results are given to schematic designer in terms of layout OA database, which he may save and then use automated scripts to extract the post layout effects and parasitics. On the top left hand, you can see how the methodology gives a preview of how the layout would look for this particular design. The schematic designer may do a right click and save it as an OA layout view for this particular schematic. On the right hand side on the top, you can see that we get an accurate estimation of area and aspect ratio for this layout topology. The methodology flow also provides schematic designer with multiple topologies based on the aspect ratio that would be preferred by schematic designer. The schematic designer may also add some constraints on his own and it would be taken care by the tool. Along with the constraints, that are identified by the tool automatically. So as you can see on the lower left corner, the tool takes care of the constraints present in analog designs like current mirror, resistors, and parasitics. And it develops a topology automatically based on the constraints identified. And also it takes care of introduction of dummy on its own. So you may add some dummies at each row or each column, and it would incorporate it automatically. And when we save it, then it might also add a guard ring based on the constraints. Here we have taken an example of bandgap circuit. So on the left hand side, we have a layout generated by ModGen manually, and on the right hand side, we have a layout generated by Animate Preview. As you can see, the bandgap reference was taken automatically by Animate Preview, and also the capacitances were identified by the tool automatically. And the layout generated by Animate Preview was DRC correct by construction. For post layout simulation estimation, we have taken a simpler design of current mirror. So as you can see on the left hand side, we have a layout generated by ModGen, and on the right, we have a layout generated by Animate Preview. So you may notice that the area is almost the same. When we do post layout simulation on the netlist extracted from from these layouts, we can see that the results almost overlap. So we know that the results generated by Animate Preview are reliable for the schematic designers. We, of course, I would like to mention that this is not a production level um, layout, but it is almost production level, which is highlighted by the results. And this layout may also be used by layout designers themselves as a starting point, and they can improve upon it as they build their layouts. So, in conclusion, we have developed this uh, methodology with help of Pulsic, which reduces the design time or the development cycle by almost 2.5 times. And once we have the routing also automated inside Animate Preview, we hope to increase this gain significantly. We were able to reduce the ECO efforts in ECO and the design cycle by eliminating the loop between layout designer and the schematic designer. So thanks a lot for hearing my presentation. Please do let me know if you have any questions.
Yeah, thank you for the presentation. Please give me a moment so that I could check the questions in the forum in which actually this is expected to be presented. So as of now, there are no questions presented in this session, but I have actually, like a couple of questions with you, right? On this one particularly, when actually you are estimating the layout area and you can say before this design particularly. Okay, so what are the how many I'm going to say how many designs or how many what are the variety of designs over which actually you have tested your algorithm? Okay,
Okay, so thank you for your question, Gaurav. So we have tested this design majorly for PLL IPs at the moment, and we have tested it for analog. I mean, it is designed for analog, but if you also want to implement this with digital layouts, and we have layouts for standard cells present, then it can place those blocks as well, and it can help you produce a layout for basically maybe both analog and digital. If you have a mixed signal design, then it is possible to generate a layout using this tool.
Okay, so Ms. Akshita, there is a question which is asked in this session by Mr. Shiv Kumar Gopal from Global Foundries. The question is, hi Akshita, animate preview will work for area-driven layout. I mean, can I use it for reducing area of layout?
So thank you, Gopal, for this question. So yes, we get an estimate of area using Animate Preview. So what the purpose of Animate Preview is to ensure that the designer has an idea of the most optimized layout area depending on different topologies that this tool sort of presents the users. And for each topology, you are given the value of area as well as the aspect ratio. So you may choose the one with the minimum amount of area or the worst case area to do your analysis on the schematic, whether you can change your multiplicity factor or number of fingers to impact the area for your layout floor planning.
Okay, okay. Thank you. Second question is by from the Bilal Iqbal from Triple IT Delhi. If layout is itself clean, why it is not implementable? This is
So
the
thank
question.
you, Virar. Yes, so the layout is DRC clean, but so it is not implementable because today we have to still implement the routing part. So it is for future work that routing is not present there. And the second part is that when the manually the user makes a layout, there are certain sort of area optimization that the user does. So this layout that Animate Preview is generating can be used as a starting point for layout designer, and they can improvise on it, maybe not use it as it is, but it is near to production. So today, the schematic designer can use it to do an estimation of parasitics and PLS effects on the design that is being created by them.
Okay. So
Sorry,
one
I
more
couldn't.
question.
Yeah.
Yeah, one more question from Mr. Vishesh Kumar from Cadence. When it gives the preview, does it consider P cells or it is just a symbolic estimation?
So thank you, Vishesh. It does considers the pieces while implementing the layout. So it picks the pieces from Techno library and it creates a layout based on those. I cannot hear you. I'm sorry, I lost the audio.
Sorry, actually, I'm keep muting myself in between so that
Okay,
there is
okay.
no, can say, so just let me check one if there's any question. So yes, there are no more questions here for you in the which are posted in question answer section. So I hand it over now the proceedings further to uh, so Senthil, from here you please take it forward. Thank you.
Thank you, Gaurav.
Yeah, thanks, Akshita. We'll move on to the next paper, which is automated generation of
Okay, and it reduces the voltage headroom of the design. And sometimes the voltage headroom is so large that design may go to the linear region that will lead to a phase noise impact in the design. And since it requires a lot of iterations at the design level, and correspondingly involvement of the layout resources would be there to uh, to converge to a one point where the design is the fully compliance. So it is a long journey to achieve that target. And another reason for this motivation is the CCO structure is across the industry are used as an inverter basis CCO, especially for the low frequency applications like till 7 to 8 gigahertz of the applications. If we have to achieve the good of the phase noise, then we go for the LC. But the scope here, we are discussing about the inverter based architecture only. So I discussed in the motivation slide that we need a solution to capture, to know the post layout effect well in advance, so that when we are simulating the pre layout data, we have almost correlation between with what we will get in the post layout summary. So how we can do that? We can do these things by using the template based flow. What is template based flow? Template based flow is that uh, since the architecture is same, the similar type of block, let's say if it is already done in the design, independent on the technology things, if it is already there, those data will be the initial inputs to estimate the sizes of the device, to estimate the parasitic impact of the devices. So how we can do this? First, we establish a mechanism. We jointly with the cadence establish a mechanism where we can store all the data in a library. The data are like the schematic designs, the snapshot of the schematic and the layout data, and the constraints is the main which govern this exercise. So whenever we have the similar topology of the design, whenever we have the similar topology design, we can reuse our data to that design. So what we are doing it here is that we are mapping all the design informations from, let's say, the already existing to the new design, and even this all the CDF property. Okay, so when the data is mapped, all the constraints are met, we can get a final the layout, which has all the placement related informations. And since our target here is that to get a extracted netlist, out of this, so the design has to be the LVS clean. So in this step, we are cleaning the LVS part by adding the tabs and the labels in the design. And when we have the post layout simulation, that is the initial point for the designer to simulate the data. So that become a pre-layout netlist on the post layout data. This is the pre-layout simulations on the post layout of the data. To go in a little deeper in this, so this is the generic pattern which we are storing as in constraints. So tool intelligently identifying matching the design, and it is mapping with the corresponding one-to-one devices, even the nets. So this the tool is doing intelligently, and how it is doing, and if we have to manipulate some of the data, we can use this file to do so. So in this particular file, we have the two sections: placement related option and the routing related options. So we have all the control to do this, and on top of this, we have the API. Where we don't need to actually go to the layout canvas and do this exercise. We can do it at a schematic design mode. Okay, so you don't need to be very schematic design don't need to be very familiar about how actually the layout is done. So we can do it in a one click button. So as a result, we have been observing that the conventional approach goes the variation from, let's say, the 20 to 40% range, based on the type of the IP. Let's say if we talk about the NFC IP, which operates where the carrier frequency is in the 13.56 megahertz range, to the 5G application PLL, where the frequency of operation goes to the almost 6 to 7 of the gigahertz range. So for the higher frequency design, the offset is quite higher. The differences is quite higher pre and post layout. Using this approach, we can reduce to the 10%. We can appreciate in this figure that we have reduced the design within a 10% of range. As a summary, I discussed, so the mismatch can be less than the 10% range, since we are getting the data from the already existing of the template. It's a very less iterative, and even the no iterations is required, and it is a and during the initial phase of the development, we don't require the layout designer to be available do these exploration. The schematic designer can do by himself. Okay, and since this layout is automatically generated, this could be initial point for the final stitching of the complete of the layout. And in this particular sections, as we have mentioned that there is a 10% mismatch. The reason for this mismatch is that the one of the reason is that since the EM is not compliance, we have not yet addressed the EM part in this particular one, because every CCO structures can have the different of the requirement of the current. So currently we have not addressed this, but we are planning to do this. Once we do this part, then I can see that the mismatch will reduce to the within a 5% of the range. So in terms of the cycle, if I talk about we do the pre-layout simulations, designer do this is a conventional flow. After that, the layout designer do the understand the constraints and develop the layout accordingly. In the post layouts netlist, as is based on the design complexity, it may require the multiple iterations to reach to a target. But using this method, we can reduce the development time. Even the post layout simulation time can be reduced to the 40%. That's all from my side. Thank you.
So thank you for the nice presentation. Let me check whether what are the questions posted in this particular forum for you. Okay. So as of now, I think a question is getting posted. It will take some time to come to the you can say the chat to the forum. So yes. So may I ask Senthil to please ask a couple of questions specifically from the presenter, or if somebody wants to ask a question now from here itself in this forum, you can unmute and you can ask question directly to the presenter. Thank you.
Hey, Rajiv, quick question. I had one question on the thing. So, when you speak about back annotation, specifically, is this okay? So, is this some sort of you're trying to study over time, and there are okay, we know there are scripts and things which have learned over time, and they kind of pre-estimate the values. Have you tried any of those? How does it correlate with pre-estimation? It's sort of like a machine learning or something. Few companies have started trying it. Is it in line with it, or is it purely you just do the layouts, you kind of put the things? What is your direction towards this?
Yeah, Samson, thanks for the question. Yeah, you correctly said that for sure it's linked with the same approach that other industries are doing. So it's for sure it's based on the machine learning. And let's say if you feed the more patterns, more templates into the design, it will be more mature to take the decision and it can give the better decision. It's going in that direction. And in terms of the back annotations, we are back annotating the same parameter which we get it after the extraction, like RMC and the let's say IDF properties which are updated after the layer.
Okay, got it, Rajiv. Yeah.
Yeah, thank you. Thank you.
Okay, thank you.
Thank you.
Yeah. Professor, do we have any other questions posted in? Gaurav?
Yeah, I was just checking that only. So as of now, there is no question. So you please proceed further to the next presentation.
Yeah.
Just a moment, I think. Yeah, I think. Yeah, there is no question. I was just checking the chat box also. So thank you, Mr. Rajiv for such a nice presentation. Uh, uh, but if Senthil ji allows, then I can ask only one question. So this precisely is the CCO. It's like in the design cycle, I'm to say how much I'm to say how much reduction the user time, the design time actually I mean to say that has been reduced specifically by adopting this method. Because you guys used at your end definitely. So what is your experience?
So my experience on that is that around 40% design cycle can be is reduced, okay? Because we have been exercising in let's say the very high frequency design, let's say 6 to 70 bars, which we are currently doing that. So by using this method, we gained around the 40% of design cycle, and that 40% is a combination of the layout and the design cycle.
Okay, thank you. Thank you, sir, for such a nice presentation, and wish you very good luck. Thank you. Senthil ji, we can proceed to the next presentation.
Okay, thank you. Thanks, Rajiv. Okay, the next paper we have is DPA, Design Planning and Analysis, a methodology to plan hierarchical design with congestion analysis to implement an automotive IP. This is presented by Priyanshi Shukla. Priyanshi is an application engineer with Cadence Design System India for about 2 years, primarily working on customization required in analog custom layout using Cadence skill language. Yeah, with that, let's get the presentation started.
Hello everyone, my name is Priyanshi Shukla. I am working as an application engineer at Cadence Design Systems. Today I am going to talk to you about design planning and analysis, which is a methodology to plan hierarchical designs with congestion analysis. And also I would like to thank Priya Mehardev from ST Microelectronics for working with me on this paper submission and using this design planning flow successfully in her design. These are the issues which designers are facing while doing the floor plan using the traditional methodology. Hierarchical designs are challenging to plan and estimate, while layout implementation for the subcells are not present, or it can be present throughout the hierarchy for few of the blocks. Using the options generate all from source, for top cell, it generates all hierarchical contents flat at the top layout view. Placement at the top level is oblivious for the all lower level hierarchies. Top level placement is based on estimation. Estimating the aspect ratio for the subcells and the top cell adds a lot of rework for the layout designer. Layout designer has to multiple times descent edit into the block for rearranging the block, which is really a time consuming task. Visualizing the flight lines between the blocks which shows the connectivity between the blocks is really very difficult to understand and is effortful. This is the traditional methodology which the designer uses for doing the floor plan. First of all, we use the generate all from source option in layout from the top level, then visualizing the flight lines which shows the connectivity between the blocks, then descent edit into the block for implemented layout view, or we plan the unimplemented views. Then we return to the top, then again we visualize the flight lines, edit the block if any modification is needed, then again return to the top. In this way the iteration continues here until we are satisfied with the floor plan. Then at last we finalize the layouts for hierarchical blocks. So this is the traditional methodology which the designer uses for doing the floor plan. This is the proposed methodology that is known as design planning and analysis. This is available in Cadence Virtuoso environment, and DPA is used here to optimize layout area and reducing the turnaround time. A design planner introduces a new concept that is known as virtual hierarchy. Virtual hierarchies are generated for the blocks for the schematic blocks that have no corresponding layout already present. Design Planner supports hierarchical schematic driven layouts. It supports hierarchical visualization, which allows us to easily view or hide details at any level for a particular selected block or for the whole top cell. Then it supports hierarchical and congestion aware design planning. It supports hierarchical routing and congestion analysis, which help us to further improve our floor plan based on the routing information. Like here we can see the schematic blocks are present. Then from the layout side, we have used the option generate all from source. So it has generated the virtual hierarchies for the subcells whose layout was not already present. These green dotted lines are known as these are the virtual hierarchy blocks. So based on the connectivity information, we will be rearranging these blocks and the hierarchical blocks. Then once we are done with the floor plan, so to further improve that floor plan based on the routing information and avoiding the congestion, we will be running the congestion analysis. So while we run the congestion analysis, the tool is internally running the global router, which divides the design into the number of G cells, that are global cells. So after running the congestion analysis, we get the histogram. So based on this histogram, we will be rearranging the blocks. Suppose we are selecting the congestion range 91 to 100%. So this is the highly congested area in our design. So we select this range. Then it shows all the nets which comes under this range. So we will be selecting the net and we will be rearranging the blocks based on this congestion histogram. So in this way we will be removing the congestion in our design based on the routing information. This is the proposed methodology flow, that is design planning flow. So we can control the display level of hierarchy and analyze the connectivity for a particular selected block. Suppose here we have selected one block and we are controlling the display level of only this particular block, and the other blocks at the same time remains unchanged. Then for analyzing the connectivity, we select one block. It shows the number of connections with the other blocks. Suppose it is showing the 10 connections with this block. So it is clear that we have to place this block near to this to have the shortest net length. So in this way we can rearrange the blocks and the hierarchical blocks by controlling the display level. Then area boundary gets adjusted after moving the instance outside the boundary. Suppose we have selected one hierarchical instance and we are moving this instance outside this area boundary. Then this area boundary will be adjusted automatically. We don't need to stretch this boundary. It will get adjusted automatically to fit this block inside this area. Then to further, these cells can be readjusted based on the congestion analysis histogram. Then once we are done with the floor plan, so based on the routing information, we will be further rearranging the blocks to avoid the congestion in our design. Then finally, once we are satisfied with the floor plan, these virtual hierarchies will be converted into the real layout using the make cell command, which is available in the Virtuoso toolbar. So this is the flow. First of all, we generate all from source. Then so this will generate the virtual hierarchies for the schematics that have no layout already present. Then we control the display level for a block or for the whole top layout view. Then we analyze the connectivity. So based on this connectivity information, we will be rearranging the blocks. Then we rearrange these virtual hierarchies. Then to further improve our floor plan based on the routing information, we run the congestion analysis. Then once we are satisfied with the floor plan, we realize these virtual hierarchies into the real layouts. Then the designer can work on the subcells, or the designers can work parallelly also for the subcells while doing the floor plan from the top level. These are the results which we have achieved using this design planning flow in our design. So area is reduced by 25% and turnaround time is reduced by 30%. This may vary with the design size. The design which we have shown in the snapshot is having the 8 number of hierarchies. So for this design, we have reduced the turnaround time by 30%. Now summarizing the presentation. Virtual hierarchies are generated for the cells which have no corresponding layout present, and these virtual hierarchies are later converted into the real layouts after we are satisfied with the floor plan. Blocks are rearranged based on the connectivity information. So it shows the number of connections between the blocks. So we can rearrange the blocks accordingly. This is the biggest advantage of this design planning. That is, we don't need to multiple time descend edit into the block, then we rearrange the block, then again coming to the top level. So this saves our time. We can view the connectivity information and control the display level from the top level itself. We don't need to descend and edit into the block. Then to further improve our floor plan, we run the congestion analysis, which shows us the routing information also. So based on the routing information, we rearrange the blocks to avoid the congestion in our design. So here the productivity gain we have achieved by 30% and area optimized by almost 25%. Thank you.
Thank you, Mr. Priyanshi, for the nice presentation. So I just check whether you have got any question posted in the forum or not. So as of now, there are no questions here. Okay. So, but I have specifically because your presentation was very interesting one when you're talking about the hierarchical design perspective and the congestion aware actually like a design optimization. So so I just want to say that what is your personal experience? To say when you go for when you utilize this design in the commercial design, then what specifically is your the personal experience in getting the you can say the design time reduction and all. How much does it impact in real life?
Yeah. So main thing what our aim is while designing the IP is to reduce the area, and with this flow we are optimizing the area and reducing the turnaround time, which is the aim before starting any IP of a designer. So this is what we are achieving using this flow.
Okay.
Yeah,
so thank you. So when you are targeting the area optimality, so the delay and power, how does it impact to that specifically? Because when we look for the design optimality, the area, power, and delay all are the concern. Okay, so if you are going it for with area optimality, then the power and the delay, how does it gets affected? Do you have any comment on that?
No, we have not went to that part for the delay and power. We have just optimized the area in this flow.
Okay, fine. So there is a question from you from Miss Nishita Dhawan from Cadence Design Systems, and her question is, "Hi Priyanshi, what was the kind of block you designed using DPA?"
This is the block, one of the IP we have taken from the one team from ST only, and we were having the 8 number of hierarchies in this block. Actually, I'm not aware of the actual name of the IP, but the number of hierarchies we have taken in this design was 8.
Okay. So one more question from my side, because you have done it for the automotive IP. So have you ever tried it with other IPs as well?
Not tried on actual design, but yeah, not tried on actual design. I tried on some of the test cases which are available in the Cadence in-house. Not tried with actual with the designer.
Great. Thank you, Senthil. It's from my side. Now the button is passed to you for further question.
Sure. I have one last question for Priyanshi before she signs off. So Priyanshi, I mean, let's say for all the sub-hierarchies, if there are a lot of analog constraints put into the schematic, let's say, the margin and digitization requirements and so on, does the DPA honor all of this and it comes up with the right area estimation, or it's still going to ignore and come up with just the base area estimation?
No. If we have suppose we have already the constraints present, we have used this flow if the layout is not already present. And if the constraints is there, that it will it will take care of the constraints as well.
Okay, thank you. Yeah.
While we are implementing the sub block, it will take care of the constraints.
Okay. Okay. Thank you, Priyanshi. Thanks for the presentation.
Yeah, thank you.
Okay. With that, let's move on to the last paper of the session. It's a compact and low power transmitter driver design for high speed SerDes system. This is presented by Santanu Sarangi. Santanu is working as an assistant professor in the Department of E&I at Silicon Institute of Technology, Bhubaneswar. He's also pursuing a PhD in electrical and electronics and electrical communication engineering at IIT Kharagpur. Yeah, with that, let's get started with the presentation.
A very good morning to all of you. This is Santanu Sarangi from Silicon Institute of Technology, Bhubaneswar. And now I am going to present my work. The title of my work is A Compact and Low Power Transmitter Driver Design for a High-Speed SerDes System. So this is the outline of my work. So introduction, so background of this work, then problem statement, what are the problem processed in the previous works, then proposed architecture, then chip implementation and measurement setup, and measurement results I'll show you. Also I will show you the simulation results, and finally I'll show the comparison and conclusion of this work. So this is the introduction of this work. So here you can see a block diagram of a conventional SerDes system. Here in this block diagram you can see three parts are there. One is a transmitter, one is a receiver, and third is the channel or medium. In the transmitter side you can see three components. One is serializer, which converts the parallel data to serial data. Again, this serial data given to the transmitter driver. Again, in this transmitter equalizer is integrated, and this transmitter drives the channel. And the clock required for this serializer and transmitter driver is generated by a clock generator called PLL. Similarly, in the receiver side, the channel output is going to the equalizers, that is CTLA and DFE. So after that equalization, this data is going to the deserializer. The deserializer converts the serial data to the parallel, and this parallel data is going for some other use. Then the clock used for this deserializer and equalizer receiver equalizer is generated by a clock and data recovery system. Now the channel, the medium is a lossy medium. So generally it's a FR4 or twisted pair cable or coaxial cable, and to compensate the channel loss, generally in both transmitter side and the receiver side equalizers are used. But we are not will not discuss this equalizer in this work, so we'll only concentrate on the transmitter driver. So here you can see the transmitter, the red arrow mark is given, that is the transmitter driver. So before going to the transmitter driver, so we need to know about what are the major parameters of the transmitter driver. So these are the major electrical parameters of this transmitter driver, that is power consumption, then data rate, then silicon area. So then our output power swing, then impedance matching, another important parameters of this high-speed data path, then loading on pre-driver, and finally equalizer integration. So this is the background of transmitter drivers. There are three types of transmitter drivers are available. One is VML, that is voltage mode logic transmitter driver. Second one is CML, that is current mode logic transmitter driver. Third one is that the pseudo differential transmitter driver. So here in the VML, voltage mode logic transmitter driver or SST transmitter driver, so it is best suited for low power applications, but it has some disadvantage, that is means impedance matching problems are there. Then integration of that equalizer is complex, and for high speed there is no less disadvantages are there. So mostly it is suitable for high speed application, better impedance matching, and then easy to integrate that de-emphasis or equalizer, transmitter equalizer, and we'll get a standard output swing. And but the major disadvantage is the power consumption and silicon area. Though a constant current is flowing through this topology, so power consumption will be there, static power consumption, and due to that heavy current, that Mn1 or Mn2, that driver transistors, so this strength is very high. So to drive this transistor, pre-driver stages are required, chain of pre-drivers, so that area consumption will be there and power consumption will be there. So that due to that, consume more power and more area also. But this topology, it's better than these two. And this one has some disadvantage, that is common mode rejection, but it is overall it is better than these two. In our work, we have used this topology, but before going to our architecture, we'll revisit some works based on this topology. I will see next. So here, this topology, particularly this architecture proposed by Canon et al. In 2005. So they have used this pseudo differential cascade structure topology, but particularly this architecture has several disadvantages. First of all, they are using 2.5 voltage supply for this because they want a high swing. But due to that 2.5 voltage supply, a heavy power consumption is there. So that again, to sustain that 2.5 voltage supply by this transistor, they are using thick gate transistors. So that cascade transistor, they are thick gate transistors. So generally, we know for thick gate transistor, the L is minimum L is length of the transistor is 5 times greater than the thin transistor. So that to maintain the same ratio, W also 5 times greater than the thin transistor W. So that overall 20 to 25 times the area increases. So that is the biggest disadvantage of this architecture. And after that, what happened due to that high W and high L, so parasitics also increases. Due to that, frequency of operation degrades. So overall, three major disadvantages are there. One is power consumption, then area increases, then parasitics increases due to that frequency of operation degrades. So this is our architecture. So as you see in the picture, so we have modified something. So here we have used 1.2 voltage supply instead of that 2.5 voltage. And again, we are not using any thick gate transistor. We are using thin gate transistor, and we are using to reduce the burden of this transistor. We are using another auxiliary path to flow the current, so that pre-driver loading on the pre-driver reduces, or will not use pre-driver anymore. So that overall due to that 1.2 voltage power consumption reduces, and due to the thin gate transistor area reduces, and parasitics reduces, and frequency of operation increases, and loading on the pre-driver reduces. And again, this particular structure helping to down this node when this voltage is high. And similarly, when this voltage will low, that time also this is high. So that again, this will be automatically down this will be low, so that it will not down. That means this node will be up. So in this way, we are getting this type of advantage. Power consumption reduces, silicon reduces, parasitics reduces, and loading on the pre-driver also reduces. And this is the simulation result of this our topology. Here you can the transient output differential data. Here you can see the I diagram. This is for 10 GB based data rate. And this is the dye micrograph and measurement setup. So here you can see overall layout. Here you can see SURDES system. Everything is there, but we will highlight this driver part. Here 3 drivers are there. One conventional driver and the previous work, and this is the proposed work. But most of the area is consumed. And this is the measurement setup, and here this is the our PCB, and this black portion is the socket. Inside that socket, our chip. So these high frequency measurement systems, measurement instruments are used for characterize our chip. And this is the measurement results. Here you can see the measured eye diagram. This is 8 GPS eye diagram. You can see this is minus 125 to 125 to 250 picosecond for 2 unit interval. For 1 unit interval, this is 125 picosecond. That means 8 Gbps. Now you can see these two results. It is that means power consumption versus data rate. When data rate increases, power consumption also increases. And this the top one curve is the for CML, conventional CML, but this is our work. So heavily we are reducing the power consumption. And here the output swing control. So by changing the auxiliary voltage, so we are the swing also changing. So that is also advantage for this topology. And this is finally, this is the comparison table. You can see they are using 130 nanometer, we are 65 nanometer, they are getting 6.25 Gbps, we are getting 10 Gbps. They are using 2 voltages, we are getting single voltages. They are getting 1 volt peak to peak, we are getting 0.8. But at 1.8 voltage peak to peak, they are consuming 42 milliwatt, but we are only using 22 milliwatt, 50% power reduction. And the area wise they are means using 220 micrometer square, but you are using only 80 micrometer square. And control swing control is possible in both the cases. And finally, in the conclusion, we have implemented a low and a compact transmitter driver. We are decreasing 50% power consumption. We are reducing 65% area, and we have successfully fabricated and tested this driver output at 8 Gbps data rate. So these are the references of this now means to do this work. And thank you everyone for giving me this opportunity. Thank you.
Thank you. Thank you, Mr. Shah. Hello. Yeah. So thank you, Mr. Sarangi, for such a nice presentation of the SERDEF. I just checked whether questions were asked for you in the forum or not. Okay. So as of now, there are no questions here. But fortunately, our session chair is an expert in this area, in the area of analog. So I request Dr. Senthil to please go ahead and please ask you questions to the presenter.
Sure. Yeah. Hey, Santanu, one quick question. See, the work that you have done is essentially using a 65 nanometer node. As you taken it forward than the 65 nanometer, I mean, is it been done in any of the recent technologies? Yeah. Okay.
Yeah. Definitely, it is possible in 40 or 28, in 22, not a problem.
Okay, see, because the reason why I kind of ask is, if you just rewind back, the node that you have developed pretty much was it, for example, the 130 nanometer for sure as a dual gate oxide, and people who try to do how do I put it, using a gate and a thin gate with a level down kind of a SerDes by default. So how does it? Okay, so my question is, how does it compare when you try scaling it down to the 16, 15 FinFET or much lower nodes? Has there been any work done in that yet, or is there a plan in pipeline to try out for coming nodes or the lower nodes rather?
No, actually, up to 40 nanometer, 29, 30 nanometer, we have seen the works, but I think it can be in that lower node. It's possible, not a problem, because for that the threshold voltage will be less also. So I have not done, but I think it's possible.
Sure. Yeah. Yep. Santanu. Yeah. Thanks. Yeah.
Okay. Thank you, Sandeep.
Okay. So thank you, Mr. Senthil, for chairing the session. And I request you to please declare the closing of the session, because we have already reached to the end of the session.
Okay. Yeah. Thanks, Professor. And thanks to all the speakers for an excellent presentation and quite a bit of engaging audience who had quite good questions. And thanks, everyone.
Thank you.
And I also thank everybody who is present here. Although it is precisely not a live event, but even after that, you can say what we have recorded. Like there is a huge presence in the session in every of the, you can say, or the technical sessions which are going on. So this is possible only because of your interest and participation and making this conference a success. This is since this is a COVID time, because of that we have to go virtual, and the COVID is still there. So I wish everybody a safe and healthy stay, and wish everybody a very good luck for your future years. Thanks everybody, and see you soon. Bye bye.
Thank you.